Now, of course, knowing so much about circuit components is useless unless we can actually build some electrical circuits. And there are two types of circuit that you need to be familiar with. There are series circuits and there are parallel circuits. Now, how you draw these circuit diagrams, it doesn't quite matter where you put the components, but I'm going to draw them in a particular way to try and help us understand how potential difference or voltage it works out across these two types of circuit. So I'm going to draw my power supply, so a cell or battery, over here, so that we can imagine its job is to increase the potential energy of those electrons. So we can think of this cell increasing that potential energy, and the amount of potential energy that each lump of charge has, that is what my potential difference is. So you can see the electrons up here at a higher potential. They're going to want to flow back down to the other side of that battery if we give them a route. I'm going to draw exactly the same for a parallel circuit, exactly the same setup. We've got a battery which is cranking up those electrons to this high potential. So we've got this potential difference across the battery. Let's pick 12 volts for our potential difference. I only pick 12 because it's got lots of factors, which makes the maths a little bit easier later on. Now, in a series circuit, all of the components follow one after the other, just like if you're watching a television series, you'll watch one episode, then the other, in order. So in a series circuit, your current would flow through one component, let's say a resistor, and then through the next component, and then carry on back the battery. Now I've got a complete circuit. These electrons can flow around. Now, we know that the electrons actually flow from negative around to positive, but we always draw circuits as if the current flows from positive to negative. We call that conventional current. It's just one of those things we got into a habit of doing before we really understood what we were talking about. So here we have our current flowing around this circuit. Now, these electrons have a high potential, so big potential difference across the battery, and they're going to drop that potential difference as they come back round. So you can see straight away that this 12 volts has to be shared between those two resistors. They don't both have 12 volts of potential difference across them. They have 12 volts in total. Now, if those two resistors are identical, let's say if I have a 3 ohm resistor here and another 3 ohm resistor here, if they're identical, they're going to share that potential difference between them equally. So they're going to have 6 volts and 6 volts. So you can see now I've got 12 volts of potential difference top to bottom and 6 volts across each resistor. These two numbers have to add up to that number, because in series, potential difference is shared. Now, if I use Ohm's law to work out what the current is in this circuit, I can say that the current will be equal to V over R. And if I look at the current through this resistor, I can see 6 divided by 3. I would expect my current to be 2 amps. 6 divided by 3. Similarly, here, 6 divided by 3, I have a current of 2 amps. And that shows me the second rule, which is that current is the same everywhere. In a series circuit, the current must be the same everywhere. In fact, if I look at the circuit as a whole, I can see that my resistances, 3 ohms and 3 ohms, will together in series, they have a total resistance of 3 plus 3, 6 ohms. So if I use Ohm's law, I equals V over R for the whole circuit, I've got 12 volts divided by a total of 6 ohms, and I end up with 2 amps, exactly the same. So resistances add together. So there are your 3 rules for a series circuit. Potential difference shared between components, current the same absolutely everywhere, and the resistances add together. If we move over to a parallel circuit, and again we imagine that these electrons are being cranked up to a really high potential, so there's a big potential difference. They want to flow downhill as soon as there is a route for them to. But in a parallel circuit, you give them 2 different routes. So here is one route through this resistor, and then another route through this resistor. now. You can see here that an electron all the way up here is going to have a lot of potential, and it is going to lose all of that as it flows to the bottom. The potential difference from there to there is the same as the potential difference from there to there. So I can say in a parallel circuit, I would have 12 volts across that resistor because it's connected to both terminals of the battery. Similarly, this resistor, it's connected straight to both terminals of the battery, 12 volts of potential difference. So I can say in a parallel circuit, potential difference of voltage is the same for each branch. Each branch will have the same potential difference. Now this must mean that some things are going to be a little bit different. So if I imagine that this is a 3 ohm resistor and this is a 3 ohm resistor, and now I use Ohm's law again and I say, well, 12 volts divided by 3 ohms, 12 divided by 3 is 4 amps. Over here, current equals voltage divided by resistance, 12 volts divided by 3 ohms, 4 amps. Brilliant. So I know the currents in these two branches, but what happens at this point here? Well, those two currents are going to combine. Just like two rivers, when they join together, you end up with the currents combining. So I'm going to have 8 amps flowing around this section of the circuit. So 8 amps of current flows out from the battery. It divides at this junction into two 4 amp sections, and then they recombine here to the 8 amps that goes back into the battery. So I can say in a parallel circuit, the current splits or joins at a junction. So current will always split or combine when it reaches to a junction. You don't need to know how to deal with resistors in a parallel circuit. You don't need to be able to work out the total resistance, but you do need to be able to recognize that if these two resistors weren't the same, that more current would flow through the smaller resistor. If you imagine a stream of water from a river gets to a rock and it's got 2 directions to go in, and one's a really wide channel, a really low resistance, most of the water is going to go that way. If you've got a tiny crack on the other side, that would be like a really high resistance, and so very little water would go that way. If this was a big resistor, this would be a far smaller current than the big current that would flow through this small resistor. And that's just about everything that you need to know about circuits.